In mathematics, a Hermitian manifold is the complex analogue of a Riemannian manifold. Specifically, a Hermitian manifold is a complex manifold with a smoothly varying Hermitian inner products on each tangent space. One can also define a Hermitian manifold as a real manifold with a Riemannian metric that preserves a complex structure. A complex structure is essentially an almost complex structure with an integrability condition, and this condition yields an unitary structure on the manifold. By dropping this condition we get an almost Hermitian manifold. On any almost Hermitian manifold we can introduce a fundamental two-form, or cosymplectic structure, that depends only on the chosen metric, an almost complex structure. This form is always non-degenerate. With the suitable integrability condition we get an almost Kähler structure. If both almost complex structure and fundamental form are integrable, we have a Kähler structure. Formal definition: a Hermitian metric on a complex vector bundle E over a smooth manifold M is a smoothly varying positive definite Hermitian form on each fiber. Such a metric can be written as a smooth section such that for all zeta, eta in EP and for all non-zero zeta in EP, a Hermitian manifold is a complex manifold with a Hermitian metric on its holomorphic tangent space. Likewise, an almost Hermitian manifold is an almost complex manifold with a Hermitian metric on its holomorphic tangent space. On a Hermitian manifold the metric can be written in local holomorphic coordinates as where are the components of a positive definite Hermitian matrix. Riemannian metric and associated form. A Hermitian metric H on an complex manifold M defines a Riemannian metric G on the underlying smooth manifold. The metric G is defined to be the real part of H. The form G is a symmetric bilinear form on TMC, the complexified tangent bundle. Since G is equal to its conjugate, it is the complexification of a real form on trademark. The symmetry and positive definiteness of G on trademark follow from the corresponding properties of H. In local holomorphic coordinates the metric G can be written. One can also associate to H a complex differential form omega of degree. The form omega is defined as minus the imaginary part of H. Again, since omega is equal to its conjugate, it is the complexification of a real form on trademark. The form omega is called variously the associated form, the fundamental form, or the Hermitian form. In local holomorphic coordinates omega can be written. It is clear from the coordinate representations that any one of the three forms H, G, and omega uniquely determine the other two. The Riemannian metric G and associated form omega are related by the almost complex structure J as follows for all complex tangent vectors U and V. The Hermitian metric H can be recovered from G and omega via the identity all three forms H, G, and omega preserve the almost complex structure J. That is, for all complex tangent vectors U and V. A Hermitian structure on an complex manifold M can therefore be specified by either a Hermitian metric H as above, a Riemannian metric G that preserves the almost complex structure J, or a non-degenerate two-form omega which preserves J and is positive definite in the sense that omega greater than 0 for all non-zero real tangent vectors U. Note that many authors call G itself the Hermitian metric. Properties: every complex manifold admits a Hermitian metric. This follows directly from the analogous statement for Riemannian metric. Given an arbitrary Riemannian metric G on an almost complex manifold M, one can construct a new metric G, compatible with the almost complex structure J in an obvious manner. Choosing a Hermitian metric on an almost complex manifold M is equivalent to a choice of U structure on M, that is, a reduction of the structure group of the frame bundle of M from GL to the unitary group U. A unitary frame on an almost Hermitian manifold is complex linear frame which is orthonormal with respect to the Hermitian metric. The unitary frame bundle of M is the principal U bundle of all unitary frames. Every almost Hermitian manifold M has a canonical volume form which is just the Riemannian volume form determined by G. This form is given in terms of the associated form omega by where omega n is the wedge product of omega with itself n times. The volume form is therefore a real form on M. In local holomorphic coordinates, the volume form is given by one can also consider a Hermitian metric on a holomorphic vector bundle. Kähler manifolds. The most important class of Hermitian manifolds are Kähler manifolds. These are Hermitian manifolds for which the Hermitian form omega is closed. In this case the form omega is called a Kähler form. A Kähler form is a symplectic form, and so Kähler manifolds are naturally symplectic manifolds. An almost Hermitian manifold whose associated form is closed is naturally called an almost Kähler manifold. Any symplectic manifold admits a compatible almost complex structure, making it into an almost Kähler manifold. Integrability. A Kähler manifold is an almost Hermitian manifold satisfying an integrability condition. This can be stated in several equivalent ways. Let be an almost Hermitian manifold of real dimension 2n and let be the Levi-Civita connection of G. The following are equivalent conditions for M to be Kähler. Omega is closed and J is integrable. J equals 0. Omega equals 0. The holonomy group of is contained in the unitary group U associated to J. The equivalence of these conditions corresponds to the 2 out of 3 property of the unitary group. In particular, if M is a Hermitian manifold, the condition d omega equals 0 is equivalent to the apparently much stronger conditions omega equals J equals 0. The richness of Kähler theory is due in part to these properties.